Hello, I'm John Voss. This is our final project for Comp 300, Data Mining and Warehousing. I worked on this project with Vasilios Christides and Grace Biasco. Before we actually go into the slides of this project, I'd like to take a look at the original data set and go over some of the changes that you will see implemented later. Here you can see our original data set. In column A, we have country code. This is just another identifier for country, and using data mining techniques discussed later on, we will remove this column. Next, over in column B, you have country name, which will become our ID, replacing country code as our current ID, since we don't want these values to be used in any future calculations and future figures. The next column to the right, column C, is titled year, and that is just the year denoted by decade from 1970 to 2010. Next over we have the column age group, and if we scroll down in age group, you'll notice that there is a few rows titled all ages. Through data mining discussed later, these rows will be removed since the data is redundant. The next column over is titled sex. You see male, female, and both as the rows. In a later iteration of this data set, we will remove the row both to get rid of any redundant data. The next two columns to the right are number of deaths and death rate per 100,000. Number of deaths is exactly what it sounds like. It's the number of deaths given a certain decade, given that age group, and given that sex. Death rate per 100,000, however, is very different because that focuses on the population of a given country. Just to give you an example of what death rate per 100,000 means, we'll take a look at a small country like Madagascar. So in 1970, for the age of 0 to 6 days, male, we have a number of deaths that is equal to 4,786, and we have a death rate of 158,853.7. Then if we look at the US, under that same demographic, we have a number of deaths equal to 25,963, and our death rate is at 77,183.7. Even though the US has almost five times more deaths, the death rate is a little more than half the death rate of Madagascar given the same demographic. This is because Madagascar is a much smaller country, so per 100,000, these deaths carry a lot more weight than these deaths carry for the US. Going back to the slides, I'm going to now pass the torch off to Vasilios.
All right, thank you, John. So I'm Vasilios, and I'll be taking you through the rest of the PowerPoint slides and taking a deeper look at our data and analyzing it a little more. So kind of a recap of before what John said was our data really looks at the effect of age, gender, year, and country on mortality and how each one of those factors, both individually and combined, affects mortality rate. We did some research and we also added war status as well to see if that has any effect on mortality. And overall, we looked at 187 countries and over 4 decades. So a lot of data, and a lot of things to analyze and a lot of conclusions to be drawn. And so now we have our filters. So kind of what we didn't go over before is, so when we put in sex as an attribute, we listed it as binominal because there are two, male and female. And so how RapidMiner handled that was for the where the category was both, it provided a null value, or it was a question mark, meaning that the value was missing. And so with that being said, we wanted to filter out everywhere where sex was missing, and so that's where the first filter is here. Additionally, in the same realm, we wanted to get rid of the age group where it was uh, all ages, because that was a calculated field and that could have been derived from the data we already had. So we didn't want that to kind of skew our data or provide us any kind of inconsistencies with how we looked at age and gender. So this is a general overview of our first process. So this is more of our pre-processing data cleaning kind of process. You can see it's couple of operators, and we'll kind of go into that more detail here. Um, first, first off, we have the roles and attributes operators, and really what the first one does, the set role operator. This sets country name as the ID. We did this because we didn't want our country name to be included in any of our later calculations or figures or anything like that. And additionally, the select attributes operator gets rid of country code because although country code can be used to identify country in the given time, uh, we just thought it was confusing and we wanted to remove it, because it also just took up space and not all of the country codes necessarily map to the country you would think of. So one of the design choices we made was we wanted to make sure that any data we manipulated we had the original version of, and so we did this through the generate copy operators. There are two of them, one for the death rate per 100,000 and one for age group. So eventually what we wanted to do was we wanted to make a scale of death rates, ranging from the lowest being 1 and 10 being the highest death rate countries. Um, and so we also wanted to keep the death rate itself, the raw number. And so we generated a copy of this, which again we will use later and explore later when we talk about our discretization process and operators. Um, and then the other thing we generated a copy was age group, and we turned that into age category. Again, this is just to discretize later age groups, so we discretize them into 5 groups: infant, youth, early adult, adult, and senior. Um, and so that would make things a little more simple, especially for the demographics where they were basically infants, 0 days to 364, and then from there on until age 4. So it gave us a more universal way of looking at things, by putting it into years, and even a little bit further than that, it put it into understandable English data, if you will. With that being said, let's go into our discretization operator. So kind of what we said before was, we created a copy of the death rate per 100,000 so that we could discretize and manipulate that data without affecting the original data. Um, and so what we did was we discretized by frequency, meaning that death rate per 100,000, which is a numerical attribute, is discretized into a user specified number of bins, which we chose to be 10, because it gives a nice scale between 1 and 10, and it didn't do anything weird, and we didn't have a scale between 1 and 7 or 1 or 6, 1 through 6. So obviously, with that being said, this created a scale for countries with low demographics. Were listed as ones, twos, and countries that had very high death rate demographics. Those were typically categorized as higher, towards 10. And so if we look at how it was broken down, we did a tree. So obviously, if you look on the far right here, to be a 1, typically you had less than 69 death rate per 100,000, and if you look on the far left here, usually had greater than 12,925, and if you know, kind of somewhere in the middle to be a 5, you had to be greater than 453, and you know, greater than 259, and then less than or equal to 802, and then greater than 146. So again, um, you can kind of see how it's broken down. We tried to make it as equal as possible, which is, you know, kind of why you see full colors instead of, you know, a breakdown, you know, in the middle or cut in half, something like that. So again, this is kind of why we chose the method of discretizing by frequency as opposed to by binning or size, because from there we would see, um, you know, that infants and elderly had higher death rates, which we kind of observe in normal society, and this would kind of skew our data, making it more specific when we really just want to make a broader claim, especially trying to compare things like sex, age, and you know, war status to these more universal statistics and numbers. So the last operator we have before we finally store our data for later use is the map operator. Um, and so we use the map operator because there is really no easy way to map ages, especially when they're not entirely numeric. As we see, there's the word years at the end, or early on, if we were to scroll up here, it says, you know, 0 to 364 days. So also, you know, between the conversion of years to days and getting rid of the actual text, it'd be very difficult to you know, kind of discretize that. So basically what we did was we mapped, you know, sets of ages to values. So for example, we see, you know, 65 to 69 years old, which were in our original data set. We said that these people are seniors, and you know, so on and so forth. Also, when we discretized in the previous step, the death rate scale, RapidMiner gave us, you know, kind of like a default, I guess, value, and so it gave us range 1, which we noticed before, and so to kind of make it more understandable and more readable, we just changed it to a simple 1, again, just to give us a better scale. And so obviously, that, you know, range 1 corresponds to 1, and range 2 corresponds to 2. So with our pre-processing done, now we can move into our more statistical and analytical data mining techniques. So really what we wanted to do was we wanted to explore how two attributes are related to each other. And so with that being said, we looked at naive Bayes. And so naive Bayes is a high bias, low variance classifier, and it can build a good model even with a small data set. It is simple to use and computationally inexpensive. Typical use cases involve text categorization, including spam detection, sentiment analysis, and recommender systems. So I don't know if there's a better option than, or a better definition than that for what we're doing here. But basically it looks at how related attributes are in comparison to death rate scale. And so the higher the rate, you know, the more correlated the attributes. So what we're doing here in this process is we have retrieve after pre-processing. Basically this takes all of the data from what we, you know, did in our cleaning and our you know, kind of preparing process, which we talked about before, and it's going to put that data into this process. The set role, this sets the death rate scale as a label attribute. This will be used by naive Bayes, so this provides the attribute that we want to compare against. So we'll see how that plays out in the results. Select attributes. We selected a subset of attributes, so you know, we didn't want everything included here. and then naive Bayes is the actual operator here, and then the weight by correlation, provided a weight by how correlated things were with naive Bayes. So if we look at the results here, um, we'll see surprisingly war status had one of the lowest correlations weights, and so one of the highest was actually the year. Again, you would kind of expect this to be a thing because over time, especially even from 1970s into 2010, technologies were changing, so you would expect that the death rate would lower over time, and so that this essentially is why this had such a big effect. Other notable ones, sex. We already know that women have a lower mortality rate than men, or at least their expected living or their expected age of death is higher than men. Um, Also, with that, the age category, seems pretty related. Um, Infants and elderly are more likely to die than middle-aged people, and so obviously, we we think that this is a good metric of how related the death rate scale was to these other attributes.
Our final test was implementing a correlation matrix. We chose to measure the correlation between year and our normalized death rate. We had initially predicted a mid to high negative correlation between year and death rate, meaning we thought that as the years increased, death rate would fall. Our predictions were rooted in the thought that with the progression of science and medicine over the past 40 years, the death rate would drop worldwide. We soon realized that while there is a negative correlation, it is so slight it is almost not relevant. The correlation was negative 0.073, meaning the death rate did drop over time, but barely. It would be interesting to see if there had been a more significant correlation from data over the past 100 years, or if it would continue to be as weak. It would also be interesting to trace the correlation decade by decade to see if there were any significant changes between very small clusters of years. Thank you for listening to our presentation. We enjoyed exploring our own data set and finding new ways to predict, analyze, and measure the significant connections between attributes.